Hey everybody, in this recording we are going to look at solving equations with imaginary numbers in the solutions, and we're starting off with a classic quadratic equation. In this quadratic equation, it already has the standard form of the quadratic equation for us set up on the right, and it's already equal to 0, so it's really in quite an ideal position. Now, typically when we're solving something like this, what we want to do is we want to try to solve by factoring, because factoring is kind of easy for us now. We're pretty fast at it. So something like this, a quadratic trinomial, or anything in this form where really the power on the leading term here just needs to be twice that of the middle term, and this one would have no variable at all. We can use something we refer to as the AC method with grouping, so on and so forth. Now, to see if this would work for us in this situation, we need to recognize what A is, which is going to be a 1 in this situation. And we need to recognize also what the C value is to get started. So the A we said is 1 and C is 4. And we're going to multiply those two values, 1 and 4. And obviously here it's very easy. We just get 4. In another example, it might be more difficult. That's why I'm being a little extra. Now, we want to find what pair of numbers, if this is factorable, what pair of numbers will multiply to give me 4, but can add or subtract to give me 2, which is our B value. Now, what multiplies to give me 4? Well, start with 1 and 4, 2 and 2. And once you hit the square root, you're really at the end of the line. Will there be a pair of factors that give me a B value of 2 when I either add or subtract them? And the answer to this is no, a big fat no. When we cannot factor something, if it's not factorable, we have to use the quadratic formula. Now, we're going to see another video that I will set up for us where it's going to be a kind of a series of maybe about 4 videos where we're going to go into solving quadratic equations by completing the square and taking square roots. And that's going to evolve for us into a master technique. So right now, let's just jump ahead because we're in Algebra 2. We learned about this in Algebra 1. We might forget some stuff and need a little bit of the gaps filled in, but we should know what the quadratic formula is. So we're going to use the quadratic formula here. Now, many of you might be like, silly, I don't need to watch you do the quadratic formula. I can plug in by myself. Maybe not. I've watched a lot of people plug in x's into their quadratic formula, and I've watched a lot of people who correctly plug in the coefficients and then don't know really how to simplify. Not only do they not know how to simplify what's in the radicand, in this case it's a special name called the discriminant, they also just overall don't know how to simplify. So let's go into this example together. The quadratic formula is x is equal, and you would always use the variable in your quadratic equation. X is equal to, and now you want to watch the length of your fraction bar of the quadratic formula as well as the length of the line of your radical where it's extending over. X is equal to opposite of b, or negative b, plus and minus the square root of, I close off my square root so I know where it ends in this situation. Usually I do that at the end. I don't know. I did it early. Square root of b squared minus 4 AC all over 2a. And when I say all over 2a, I mean all over 2a. I grabbed a calculator so that I could even show you an example today, and whether it's this recording or another one, where I'm going to show you how we type it in the calculator just to make sure we can all do it. And I'm going to ask you to do it too. So when that's going to come up, I'm going to ask you to press pause, grab a calculator so you can do it with us. Please don't use your phone calculator. No good. No bueno. Get a real one. So let's fill everyone in. A is 1, B is 2, and C is 4. X equals. Now, do I have enough room down here? I think so. I could scooch up a smidge, and let's go from there. X is equal, actually, before I continue, the directions in this situation say find all solutions. previously we had seen directions that said find all real solutions. When we transform from a scenario doing find all real solutions to find all solutions, we're really transitioning into a position where we are finding both the real and the imaginary solutions, which hopefully we're kind of getting that from the title of the lesson as well as the title on the page and all that. So be a good critical reader, pay attention to what the directions say. They really give you a lot more clues than you give them credit for. A lot of you don't even read the directions, so yeah. Negative b, so that would be opposite of 2, plus and minus. So I don't think everyone really understands the plus minus. The plus minus is really consolidating two equations or solutions into one compact formula, so we don't have to write it twice. So if you have John Smith and Joe Smith, you might consolidate and say John and Joe Smith, kind of like that. B squared, the b is positive 2 in this case. Even if it were a negative 2, it wouldn't really change anything at that part because both 2 squared and negative 2 squared are 4. Negative 4 times a times c. Now, I don't have dots here for multiplication. You want to put dots? You want to put parentheses? Go nuts. They all mean the same thing. Don't get weird. A is 1 and c is 4 all over 2a, which is 2, times 1. It's a little squash low. Sorry about that. Now, let's continue up here. So I'm going to draw an arrow showing where I'm going with my work. The equal sign is here. I've seen people put equals 0. Don't do that. That's not a thing. That's not what we're doing. We're solving for x here. And now let's continue. So we have x equals negative 2 plus minus the square root. So let's start cleaning up what's inside this radical. 2 squared is 4 minus 4 times 1 times 4. If I cover up, please don't think I'm going too babyish because I'm going over this because people mess this up. So just assume I'm talking to you. I'm going to cover up the minus. If there were negatives involved here, obviously the 4 here, it's like minus a positive 4 or plus a negative 4. You choose which way you want to interpret it. I'm going to think of it as minus a positive 4. So I'm covering up my minus and I'm looking at the 4 times 1 times 4, which is 16. All over 2 times 1. In this case, it's just a cute little 2. When you're subtracting and they have different signs, again, I'm not trying to be babyish, but some of us need this. 4 minus 16. I have a positive 4 and a negative 16. You subtract them in the easy way, whatever is bigger. And in this case, 16 minus 4. And then you take the sign of the number that's bigger and stronger. So the 16 is our bigger, stronger number, ignoring the negative, which is negative. So my answer will be negative. Hopefully that makes sense. So x equals negative 2 plus minus the square root of, that would be negative 12. All over. Not just what's under the radical, not just the radical, everything, okay? All over 2. Continuing bit by bit. Don't try to do it all at once. I'm showing it in steps. You should show it in steps. Plus, minus. Okay. We have a negative under our radical. We should already know that the negative or negative 1 in a radical is equal to the imaginary unit I. So the square root of a negative 1 is equal to imaginary unit I. So if that comes out, the only thing left inside will be the 12. So I have a negative 1 in there. But what really is 12? Well, let's go full blown in this and really break down this example. There's a negative 1 for sure. Now 12. 12 is even, so let's start with 2. 2 times what? 6. 6 is also even. 2 times what? 3. Amazing. Best thing I ever saw in my life. All over 2. Takes a pair to make a square. 2 by 2 or 2 times 2 makes a square. If you saw dimensions of a piece of lumber or a poster or a picture frame that were 2 by 2, you should know that those dimensions represent a perfect And when we want to find the root of that square, the number that was squared off, well, we square root of the pair of 2's is 2, right? So almost done. X equals -2 plus minus. So that 2 comes out, and the -1 comes out as the imaginary unit I, square root 3 all over 2. Almost done. We want to simplify this. We're going to simplify using our famous pretzel. I'm going to use a purple pretzel. So where is this purple pretzel? I'm going to look for something I could simplify. Typically when I do quadratic formula, I try to find something that I can knock out of both pretzel ovals that matches, okay? I don't need to reduce this into one thing and this into something else, like only take a 2 out of this and not take anything out of that, and then make 2 separate fractions. I want to say to myself, what does everything have in common? This delicious, happy pretzel. Well, it looks like I could take a 2 out of everyone. I'm going to reduce the 2 all around. So what's next? Last but not least, if I knock a 2, and a 2 out, we don't touch the radicand. We don't touch the thing in the radical. These don't turn into zeros. They don't go away. They don't cancel. That's not the word. They simplify or they reduce and they become 1. X equals, so in that case, it's actually specifically -1 plus minus I square root 3. And now it's really all over 1, which I'm not going to write down because that's just not necessary. So here we have found 2 answers. They are 2 imaginary or complex solutions. The imaginary component is the I radical 3, and the real part of it is the -1. If you remember talking about the proper form of a complex number is A plus BI. So A is -1, and the BI, well, there's 2 answers here. -1 plus I square root 3 and -1 minus I square root 3. So depending how we look at this and how we write it, if I could just maybe scooch up a smidge more just to show the 2 answers again. If I wrote them in the form A plus BI, I have -1 plus square root of 3. I'm going to make sure I close off that radical, I, and so there I have one answer. And the other answer, -1 minus square root of 3, I as well. Now, hopefully you can tell by looking at this, you can realize why it is that we don't write the I after the radical. It's going to look like it's going to accidentally fall under the radical. We don't want that to happen. It's just by being in front, we just know they're being multiplied. We're good to go. And we also see how silly it is and annoying it is to write 2 different answers when where they differ is really only in this one place, and we can't combine anything. In the event that we don't have an imaginary number and we want to find either the decimals or b squared minus 4ac turns out to be a perfect square, like 1, 4, 9, 16, 25, so on, then we would split them up so we could find the 2 different answers, whether they are going to end up being, nice whole numbers or rational numbers, a nice fraction, integer of some sort, whatever. Then we would split it up and look at it there, but we'll look at that in another video. So keep that in the back of your mind. So that is what we have. We have solved and we found all solutions. We had 2 imaginary. The biggest power in my polynomial equation, the largest exponent or the degree, was 2. That's exactly how many answers we have. We have 2 answers. Also, imaginary solutions, when we solve a polynomial equation, imaginary solutions have I in them, right? So do other irrational solutions that starts with the letter I. So imaginary and irrational, keep this also in mind. We have 2 I's on our face, so they always come in pairs. Irrational solutions, so if it was no I, if it had a square root 3, they come in pairs. What would it be? -1 plus and minus square root 3, pair. Or the imaginary, -1 plus and minus I square root 3. Imaginary and irrational solutions will always come in pairs, like the eyes on your face. So there you go. I hope that you are okay on this example. I'm not a fan of that. I think writing it like that is beautiful. And I hope you're able to do something like this on your own. And I'll have a thumbnail pop up or a little click through of another example. And let's keep it moving and see a whole bunch of variety when solving polynomial equations with imaginary numbers. All right, adios.